Good morning, everybody. My name is Riq Parra. I am a fairly new program manager here at AFOSR. I've been here 8 months, so I guess I'm a little older than you, Jim. And it's my pleasure to talk to you this morning about a sort of a new portfolio that goes by the name of Ultrashort Pulse laser matter interactions. So we're going to talk about lasers, not just any lasers, but pulse lasers. Now, you may not already realize it, but you're all probably very familiar with short pulse lasers. In fact, let me show you a picture of what one of these things looks like. So we're interested in short pulses, extremely short pulses. In fact, pulses that last a mere fraction of a second. So if you keep in mind that, say, light travels about a foot in about a nanosecond, and you look at these pulses, these are actually not all that short. They last about roughly, I would guess, about 100 nanoseconds. So the pulses that we're interested in are sort of in the femtosecond scale. So we're looking at pulses that are 10,000 times shorter than this. So roughly from beginning to end, these pulses are roughly about 30 micrometers long. So this is about a third of the width of a human hair, just to give you a sense. So let's take a little closer look at what these things look like. And sort of the goal, the objective of this portfolio is to really look at the whole broad range of phenomena that's accessible by looking at the interaction between ultrashort pulses and matter. In fact, we want to look at a couple of properties in detail. So we are looking at light sources that exhibit extreme bandwidths, sort of a whole range of peak powers, and as well as sort of very extreme sort of temporal characteristics, very short pulses. So these sort of three characteristics lend themselves to sort of what the portfolio subareas are, which is optical frequency combs, high field science, and attosecond physics. Okay, so why do we want to do this? Turns out that ultrashort pulse lasers have already had quite a bit of impact across a whole range of different applications. Now, I'm not going to go through all of these. They're here really for your offline reference. But I will make a couple of points sort of to generalize this. If you understand the bandwidth of your laser, this has a lot of implications for metrology. And that's sort of the upper right one here. So up here. If you understand the time scales of your lasers, that has important implications for material science. Now, if you understand how you propagate this through media, so say through air, that allows you to work at range. And clearly, this is something that's of interest to the Air Force, but in fact, it's of much wider interest. It's of interest to the DoD in general. And if you understand your electric field, your high peak powers, now it allows you, so these two areas, it allows you to convert your visible or your infrared light to just about any other form of photon and particle radiation. Okay. So, and this is all enabled by these ultrashort pulse lasers. So how do you make an ultrashort pulse lasers? And I mentioned this a little bit yesterday, so I'll repeat it. So if you have a standard sort of laser cavity, such cavity is going to support a whole range of modes, shown here as kind of like these little lines here. And typically these modes sort of don't have really a particular phase relationship between them. So you can bring in an element known as a Modelocked. It's an intracavity element, and you can actually set up a phase relationship between the modes, such that there'll be a point where all sort of the peaks will all line up, and you'll have constructive interference. And this happens in this picture sort of 2 times, and everywhere else in the middle, there'll be some degree of destructive interference. So if you look at the output of such a laser cavity, what you get is a train of short pulses. In fact, femtosecond pulses you can. So these are sort of the so-called Modelocked femtosecond lasers. And this is roughly what one would look like if you were to call up or go online and order one for yourself. Okay, so I want to have sort of 3 sections to my talk. And the first one is I want to discuss how you use these Modelocked lasers as essentially for their bandwidth. So as broadband phase coherent optical sources. So this is actually, I want to start with talking about an effort that's out of our propulsion directorate. This is led by Dr. Jim Gord, and he's interested in using these pulses really to look at, to do spectroscopic techniques to investigate the physics and chemistry of reacting flows. So here's an object that maybe we may be interested in. This happens to be an F-119 Pratt & Whitney engine. It's clearly an afterburning turbofan engine. Okay, I had to memorize that. But what we're interested in doing, we would like to sort of go in here and maybe sort of in real time be able to say something about the species that are being created, maybe the temperatures, the measurements, and maybe one day hope to be able to generate pictures or movies, high bandwidth, high rep rate movies such as this of the inside in real time. So this is what we're trying to do. We would love to sort of, and this is, I'm quoting Jim now, we want to measure everything, everywhere, all the time. So sort of a lofty goal. But if we are able to do that, then now we can think of generating really high rep rate, high bandwidth data that not only gives us, helps us in concept development, sort of in the R&D stage of making these things, but also in assessing the performance of such devices, as well as possibly thinking about control and feedback. Okay, so let me give you one example of one technique that they've been able to develop to do something like this. So this is a technique, it's a nonlinear technique known as anti-Stokes coherent Raman scattering, or CARS for short. And in this technique, they've been able to essentially develop they've been able to measure temperature in a single shot in one dimension in flame. So this is sort of what a typical setup would look like. Like I said, it's nonlinear, so you have sort of a combination of your beams, and you sort of focus it in a one-dimensional focus on your flame, and you get a signal out. This is the CAR signals that you're going after. This is where the information is going to be. And such a signal looks like this. It's spatially and spectrally resolved, and it gives you these sort of two-dimensional plots. So again, in the vertical direction, that's the distance. So we're actually looking across the flame. And if you take a line out somewhere in here, and in fact, these pulses, a little technical detail, they're actually chirped. So the frequencies are sort of, there's reds in the front, blues in the back, and that actually allows you to map the wavelength to time. But nevertheless, so if you take a line out, you get traces that look like this. And in fact, you can actually sort of match, you can actually fit this coherence, and as you can see, you can have pretty good fits, and the fits tell you the temperature of the flow at that moment. So you're actually measuring the temperature. So there's two pictures here. The top one is sort of a 16-shot average for reference, and the bottom one, which looks pretty good, is a single-shot measurement. So this femtosecond CARS technique that they've developed, it's happening at kilohertz rep rates. Conventional methods to do this tend to be at the hertz level, so you get essentially over a 3 order of magnitude faster data rates. Like I said, you're actually doing one-dimensional measurements as opposed to point measurements, so that's pretty interesting. The fact that these pulses are so short, essentially nothing is happening, nothing is moving during the time that you're making your measurements. And because of that, these measurements are free from collisional broadening effects. Now, you have actually exquisite control on the timing of when these beams sort of interact, and that actually results in essentially removing all sort of non-resonant background from your signal. So you get pretty good signal to noise. Another technical detail, turns out that because it's a 2-photon process, your entire bandwidth contributes to your signal. So you have very, very strong coherences. So this is just one instance, one example of how sort of these particular tools, these ultra-short pulse lasers, are really changing the game for folks that are interested in looking at this. Now, if you want to know a lot more about how to measure, combustion and propulsion flows and things like that, then I invite you to listen to my colleague Chip-In Lee. He's going to be talking about a lot more of these things later on today, I believe. Okay, so what else can you do with your bandwidth? So earlier I talked about sort of a laser cavity. You have these modes. They're sort of locked together, playing nice. But it turns out that these modes typically actually are free to sort of drift around in frequency. And that's okay, for the things that we're doing here, that's okay. But it turns out that you can actually, so in addition to that problem that it's drifting around, if you don't have a tight control on your laser cavity, these modes will actually sort of expand and contract, sort of like in an accordion, which in and of itself is also not a big problem. But if you want to do more, you want to take care of these two sort of drifts. So one of the things that you can do, and I'm not going to really go through the plot, I only want to highlight that you can actually phase lock your repetition rate to a microwave reference, and this is actually fairly easy and routine to do these days. And now what that does is it locks sort of this, it actually removes this accordion movement that I'm talking about, and it gets your modes to be sort of equidistant from each other and not moving. And then you can lock down something known as the offset frequency, and what that does for you is it actually takes this set of lines and actually fixes it to essentially 0 frequency. So now you've turned these sharp spectral lines, this comb, into a real optical frequency ruler. So this is known as an optical frequency comb. And in 2005 was the reason it received the Nobel Prize in physics. So this is interesting. Now, it immediately found lots of applications in sort of metrology. So depending on sort of how many teeth you have in your comb and actually how much bandwidth, and these are to some degree independent, and you can control it. You can do things such as coherent LiDAR, ranging. In fact, you can actually do optical arbitrary waveform generation. Because if you can measure your frequencies very cleanly and very accurately, and in fact, you can do it up to like 15 digits, it means that you can also measure time and you can measure distances very well. So on the other side of sort of this application fan, you can do things like optical clocks and time and frequency transfer. So this is very interesting. Now, very, very recently, people have been able to generate these combs. So normally these are sort of tabletop systems. You saw sort of the picture earlier of what one of these things looks like. But they've been able to do this actually in very small, compact, on-chip platforms. And this has become sort of a, I would say maybe a new field called microresonator-based frequency combs. So this is roughly what these things look like. So here's 3 examples on the very top of what these little microresonators look like. And they all generate sort of this comb type of structure. And these are potentially very interesting systems that give you high fractional bandwidth. So on the vertical scale of this sort of somewhat busy plot, I admit, that's kind of how much bandwidth you have. And these, because of their sizes, give you a pathway to having sort of line separations that are 10 to 100 gigahertz, so they're easily addressable. And this is a sort of a little application space where people have a lot of interest. Now, why do we care about this? Well, it turns out that the physics behind the generation of these combs is actually very different from the way you would generate a comb on a tabletop system. And it's actually, I would say, sort of not entirely all that understood. So now we're looking into this, and I can say on the very bottom of the slide that this is actually one of the FY12 BRI topics. So we're very excited to look at what's going on here, and hopefully next year to say a little more about it. Okay, so with that, chapter 1 is done. Let me talk about the second thrust, which is we want to now use these mode-locked lasers as high peak power sources. So this is what we call high field science. So let me bring this plot somewhat busy, so I'm going to spend a few minutes on this one. So what I'm plotting here on the left is it's a timeline, and I'm plotting for tabletop systems the achieved focus intensities of these systems. So we start all the way to the invention of the laser in 1960, and then we go all the way to today. And sort of the record is, may not mean anything to you, but it's 2 × 10⁻22 watts per square centimeter, which is a lot of intensity. Now, if you are all the way down here, so this is where all of your nonlinear optics sits. So this is where you have systems where you have bound electrons and you're exploiting the nonlinearity of your system. If you start increasing your intensity, now you start getting to the damage thresholds of materials. And then you open up the whole concept of doing laser ablation of solids. And then after that, you can think of doing laser machining and laser patterning. And I'm not going to say too much about that. I'll say something, but not too much. But it's very interesting because these things machine and pattern in completely different ways than other lasers do. Now, if I continue to increase my intensity, now I actually start freeing up electrons in my system. So my electrons are starting to ionize. And now I start creeping into sort of plasma physics. And in fact, what happens is if I start propagating these things in air, we actually very quickly generate plasmas, and we get things like filamentation. And I'll say more about that in a second. If I keep on turning up this, now we're all the way in plasma, and you get all sorts of really interesting interactions. Now, the way to think about what's going on is ordinary matter, when irradiated with these sort of electric fields, will almost immediately ionize. And then so you have these electrons, they come out, and they actually are left to sort of quiver, and the laser's still on, so they actually left to quiver and gain energy from the laser field. So as you go up in this intensity, oftentimes what you're seeing is sort of the effects of sort of these electrons quivering, and then that then leads to sort of the subsequent interaction physics. So if you go up, you start being able to do things like generate coherent X-rays or EUV. You can actually generate hard X-rays, and you can even generate protons. Now, if I keep on going up, so I'm still sort of down here in the sort of the plasma, we have these electrons that are quivering around. So they start quivering real fast. In fact, they quiver so fast they become relativistic. So this is an area where you're now seeing relativistic effects of the electrons. And this then opens up an entire new set of really exotic interactions. I mean, these have been known for quite a long time. So you have things such as laser wake field acceleration, where you can actually accelerate these electrons to sort of GeV scales on the scale lengths of about a centimeter. So that's roughly, to give you an idea, if you were to do this in conventional accelerators, you would need sort of kilometer scales to do the same thing. Now you can do this in a centimeter on a tabletop. We could do this up here if we had one of these things. So very interesting. Then if you keep on going up, now you have these ions, which normally are so massive that they don't really move all that much. We don't really pay too much attention to them. But now they start quivering, and then at some point they start quivering relativistically. So now we're really at the footstep of just the, I'm not even sure what's going to happen when we start looking at these things, to be honest with you. And there's a couple of schemes out there to really push that intensity all the way up. And then you see all the way up here at 10 to the 30, things like nonlinear QED. I won't say anything about that, but really interesting physics. Now, so if I want to use some of these high-intense laser pulses, where would I go get one of these? So if it was a while ago, if I wanted to do one of these things, I would actually have to go to a laser facility that was the size of a building. And I could achieve, so this is back in '98, I could achieve 1.5 petawatts. That's a whole lot of intensity. But I would get maybe a few shots a day on a really, really, really good day. More often than not, I would maybe get one single petawatt shot per day. These systems have, in fact, here's a picture of one of these systems. It's hard to see on the screen, but there's a person on some sort of like machine sitting somewhere in there, really tiny. These things have become smaller and smaller and smaller. In fact, they've become commercial systems now. So you can go online and actually buy one of these things. So in fact, Dr. Russell, if you want later today, we can go online and get one of these for us. And in fact, these things, what's that? Maybe. 660 joules. And one of these things actually fits in a couple of tabletops. So literally, it would fit in front of this room. And this thing would deliver 1.3 petawatts, okay? And not only would it deliver 1.3 petawatts, it would do it at a rep rate of 1 hertz. So every second, you would get one of these shots, as opposed to getting one shot per day. So this fundamentally changes the paradigm of how people are going to do sort of science here. So now every university, you can think of having one of these in the near future. So 5 years from now, this is going to look completely different. Okay, so we're interested in exploring, like I said before, the whole range of intensity. I sort of went up sort of that ladder. So let me start, again, let me go back down. Let me go back down to sort of the lower intensities. Let's talk about using these pulses to do sort of micromachining and patterning. So essentially to do laser-solid sort of interactions. And it turns out that, like I said, these things really open up a whole bunch of really interesting possibilities. And in fact, there's all these laser processing and surface texturing techniques sort of generate these very complicated nanoscale and micron scale structure. And they lead to really interesting properties. In fact, on the top right, this is an effort out of the University of Rochester, Dr. Chunlei Guo. He, a few years ago, this was reported actually a few years ago, he was actually able to generate black metals, so the most absorptive materials ever because of this interaction. He's now, since then, he decided to try different colors, so he's actually been able to colorize metals. And in fact, not only can you do things like that, you can actually create these super wicking surfaces. So in this picture here, if you put a little drop of water at the very bottom, this drop of water will shoot up against gravity. And when I say shoot up, it won't like slowly creep up, it will literally shoot up. And the reason for that is because you've created sort of an array of parallel microgrooves on the surface that generates a very strong capillary force. So again, this is very interesting results, and it opens up sort of the imagination to possibly tailoring surfaces to whatever you want to do. But the reality is that the physical mechanisms behind what causes these things are really not all that well understood. Most of the studies are still, I would say, sort of empirical, highlighting sort of the phenomenology rather than sort of so this is something that we're interested in, we're looking at to sort of bring some sort of mathematical rigor and understanding, again, with the hopes of maybe one day you could actually tailor the surface. So you would tell me, hey, I want something that does this, and then I could go to my laser and then tune something and say, okay, I'm going to give it to you, and I would know exactly how I did that. So that's this effort. So now, okay, now again, I'm going to turn that intensity back up a little bit, and now I'm going to ask the question, hey, I want to propagate these things in air, because again, if I want to work at range, you're going to have to address this at some point. You can't just work in vacuum. Now, it turns out, of course, this is of interest for people that want to do remote sensing, imaging communications, and I'll say remote interactions, and you can imagine what that could mean for people. When you do this, like I said earlier, you immediately create a plasma. It turns out that there's a phenomena where when the intensity is high enough, you get something called self-focusing, so your beam actually wants to focus on you, which is not good, and you create this plasma. But then the plasma actually wants to refract that beam out. So it's this combination of wanting to focus in and wanting to refract out that actually balance each other. So you get that high intensity spot to actually travel. So rather than just being focused and then going away, it travels for a long distance, and this is known as a filament, and it can actually travel for kilometers. So this is of high interest. A lot of people have been looking at this for a long time. In fact, I would say that currently there's two MIRIs. One is the one that RJ mentioned yesterday. There's one out of ARO looking at this, and there's efforts from JTO looking at this. And of course, we have our very own filamentation team. This is an effort out of RD, led by Pat Roach. And our team is engaged in looking at this problem both experimentally, theoretical, like pen and paper theoretical, and computational. So they have a GPU computing enclave that's building these computational models to do the propagation. And what's really remarkable, and again, few universities have this, they have access to a kilometer scale test range. So this is really interesting, very exciting, and we're looking forward to see what comes out of this. Okay. As a companion effort, this is an effort out of the University of Arizona. We are looking at other ways to maybe control these filaments. So if you look it's hard to see on the screen, but if the top picture here is if I look at a filament created by just a single femtosecond laser shot, right? And in fact, if I actually add 100 of these laser shots, believe it or not, there's actually a tiny little filament in here that's very hard to see, but it's there. If I now follow that filament, that femtosecond laser shot with a more energetic nanosecond scale laser, then you see an over 200x enhancement in the plasma density. And now you can, I think, very easily see the filament on the bottom one. So the concept of doing multiple pulses to try to increase the density is something that we're looking at. In addition, one of the things that hasn't been explored all that much is maybe doing laser beam engineering, looking at the beam profile. And typically we like Gaussian beams and we use Gaussian beams. But there may be other beams such as vortex beams or high order bezel beams that will give us different degrees of freedom and may help us localize these filaments in space. So this is very interesting work, and I look forward again to saying a lot more about this next year. Or to whomever wants to call me up, I'm happy to talk about this. Okay, so now I'm going to switch gears and I'm going to go that intensity a little bit up, a little further up. So now we're ionizing, and now you get into a phenomenon known as high harmonic generation. So what happens here is that the electric field that your electron sees is strong enough that it actually disturbs the Coulomb potential that it normally experiences. And what happens as the field goes up and down is that this Coulomb potential, which is normally flat, starts tilting. So on half cycle of the field, it tilts in one direction, and the electrons now, because it's tilting, they're now free to tunnel, ionize out of your atom. And this is what's happening in this little picture here. Your electron tunnels out. And then as this field reverses, it's going to tilt the opposite way. So this electron, which is now outside, again, gains energy in the electric field. And then when your potential flips the other way, it actually rolls back down, kind of like a marble on a surface, and it actually slams back into the parent atom. And then that releases a photon. And typically, it's an extreme ultraviolet photon. Now, this has been done for a long time. People have been doing this for a long time. And in fact, it's actually fairly easy to do. All you need is to focus your laser onto a gas jet, maybe with xenon or argon or something else. The trick is you want all your atoms to emit at the same time in a coherent fashion. And people have learned how to do that. This is known as phase matching, high harmonic. And what comes out of this, it's a nice X-ray beam that has a very nice beam profile, is very well collimated, and it's actually coherent. So this is a laser-like X-ray beam. It's not an X-ray laser, but it's a laser-like X-ray beam. And in fact, very, very recently, and this is work that Margaret Murnane has done, and RJ alluded to this yesterday, they've actually been able to generate KeV X-rays, coherent KeV X-rays out of these devices. So this is very interesting. Now, why am I talking about this? So I'm setting up this next effort. This is an effort at the University of Colorado. So now you have this high harmonic generation, and now I do something really, really interesting. I put a cavity around this, okay? So now this is known as intracavity high harmonic generation. So I put a set of mirrors, sort of a complicated looking cavity, And now I put my laser, my gas jet in the cavity, and now I'm able to, I focus the laser onto the gas, and I'm able to generate these high harmonics. And then I have sort of a really unique, novel little pickoff mirror that's able to sort of extract my harmonics out of this laser cavity. The advantage of this is now that I'm generating harmonics at the rep rate of my driving laser. So this is something that a lot of people, that's useful for a lot of people. So if I look at this beam and I say, okay, what does this look like? So this is sort of what you get. It actually turns out, because of the physics, that you get actually the odd harmonics. So you get sort of a little beam at the 9th harmonic. So now this is sort of a grading. So these are actually a split, spectrally split. So you get the 9th harmonic, the 11th harmonic, the 13th, and so on. So this is in wavelength, in nanometers. You're looking at things that are sort of 100 nanometers and below. So the one over here to the left is, say, 47 nanometers. So now if I take a closer look at, say, number 13, and I look in there, and sort of just take my word for it, because we did this with this cavity, and if I look closer in there, it turns out that when I look close enough, I actually see a comb structure, a frequency comb structure. Now, people have suspected this for a long time, but it's only now, and this is very recent work. I mean, this is, I think, published within maybe the last month and a half. For the first time, they've been able to actually show that there's a real comb sitting in there. And remember, when you think comb, you think, oh, metrology, all kinds of interesting applications. So how did they show this? Well, they actually went in there and said, okay, well, let's actually use this for metrology. Let's see if we can sort of characterize some transition that's there. So they looked at a particular transition in argon, and what they did is they took one of these teeth of this comb and actually swept it back and forth across this transition. And what did they see? Well, they saw this plot on the left. So this is an actual sort of scan of a argon transition at 82 nanometers. So this is the first time where you now have been able to do ultra high precision spectroscopy below 100 nanometers. So this is, I think, remarkable. This line width, the upper bound on the line width is about 10 megahertz, and at this point is really limited by the thermal motion of the atoms that they were looking at. So this is interesting. And one of the interesting potential uses of this is we've talked about atomic clocks, and Tatiana sort of mentioned this yesterday. One of sort of the really, really far off schemes out there is to base future clocks, rather than on atomic transitions, to do it on nuclear transitions. And if you want to do something like that, these transitions are going to be in sort of this spectral regime. And right now, and we don't have any real way to find them and characterize them, not even to say, like, how do you lock onto them and use them for your clocks. So this scheme may give you a pathway to maybe realize some of those concepts. Okay. So now I'm going to turn that intensity all the way back up, and I'm going to tell you about an effort out of the University of Nebraska that I'm really excited about. This is work by Don Amstadter. And remember, I talked about sort of these things becoming commercials. Well, it turns out that they have one of these systems. It looks something like this. It's known as Diocles. They got a great website. And this system, it's capable of putting 3.5 joules of energy in a laser pulse that only lasts less than 30 femtoseconds. And they do this at 10 hertz. So 10 times a second they can do this. So they get 100 terawatts of peak power per shot, and a really, really high beam quality. And this is a focal spot measurement done at full intensity. So it's, I mean, really beam quality, really high beam quality. So, and for those of you that maybe have worked with these kind of lasers, this is a remarkably compact laser and a remarkably clean room. Normally, it doesn't look like this. So this is quite fantastic. So what can I do with something like this? So one of the really sort of interesting notions out there is via a process known as tonsum scattering. It's actually relativistic tonsum scattering. You can actually, and the way that concept works is you can actually take your driving laser, you generate a beam of electrons, and you can actually take a little bit of that driving laser, that infrared laser, and you can actually scatter it off of this electron beam that you've created, and you can upconvert that infrared pulse all the way to the X-ray. So this is a pathway to possibly creating a beam of tunable, monochromatic X-ray, almost gamma rays. So if you do sort of a back of the envelope calculation, you can sort of, and just take my word for it, if to give you a sense of the numbers, if you scatter off of a 300 MeV electron beam, you can Doppler shift your 1 EV energy laser photon all the way to about 1.5 MeV. So you're getting into sort of gamma ray generation. Now this process is really a two-step procedure, like I alluded to. First, you got to create a nice clean electron beam, and then you have to sort of backscatter your infrared. So you're kind of once you do this, you're sort of using sort of a light bullet to hit an electron bullet in mid-flight. So it's a little challenging, but they've been able to do the first part of the step. So here on the bottom is actually a picture of, they've been able to generate a monochromatic beam of 700 MeV electrons. You really only needed 300 to do what I said before, but here they have over 700 MeV. This is monochromatic, as you can tell by the spot, and it's actually tunable. You can go from 100 MeV to 800 MeV, and it has very low angular divergence and essentially no background electrons. So we're halfway there, and they're looking now at doing the other half, and currently proof of principle experiments are underway. Now, let me say one more thing about this effort. They recently just finished an upgrade to the laser system, and they now are capable of delivering 0.7 petawatts at 0.1 hertz. So every 10 seconds, they can deliver 0.7 petawatts. And this, in many ways, is sort of the first petawatt-class laser in the US that's truly repetitive. Like it's truly, by design, gives you high rep rate. So we're excited to say, hey, can we take this 0.7 petawatts and go back to this scheme and see what we get? So we'll be very excited to see what happens. Okay, so that was that second chapter. So now there's no clock showing, there's the clocks. In the 9 minutes, plenty of time. In the 9 minutes that I have left, let me tell you about the last thrust of this portfolio, which is to use these mode-locked femtosecond lasers again, but now to generate extremely short EM pulses. So this is sort of the field known as attosecond physics. So to motivate this, I'm going to go back to our high harmonic generation. So here's kind of the same picture that I showed before, but I think a little bit simpler, showing your Coulomb potential being distorted and sort of going back and forth, and your electrons coming out and slamming back in. One of the things that I didn't mention, I purposely didn't allude to, is the fact that this process happens at least in the way I've drawn it here, at every half cycle of your driving field. So it's really happening in sort of in the sub-femtosecond timescales. In fact, it happens even faster than that, because an electron released out here, it's going to do its flight, and there's going to be only a very small window, say over here, where this burst of EUV is going to come out. So in fact, turns out that burst only lasts attoseconds. It's very, very short. Now, there's a whole bunch of engineering, laser beam engineering, that you need to do on your driving field in order to do this. And people have spent a lot of time. There's been a lot of work that's gone into this to do this sort of really complicated engineering to try to essentially, rather than getting a burst at every half cycle, because that you may not necessarily want that, to generate an isolated attosecond. So people sort of know how to do this. It's a little complicated, and you have to do really interesting techniques called polarization gating and so forth. But people can do this, and you can actually now reliably generate isolated attoseconds. Now, measuring these things is a little challenging, as you can imagine, but there's, again, some fairly mature techniques nowadays that are equivalent to sort of streaking cameras, if you're familiar with those. So you end up, if you wanted to measure, say, that particular attosecond pulse, you get these plots, these streaking spectrograms. They look sort of like this, and then from that you can actually back out via algorithms what this pulse, what the pulse intensity and the width and the phase would have been. So for this particular one, so this is a result that came out back in 2008 from Germany. They were able to show that they were able to produce an 80 attosecond burst, and in fact, they actually got this in the Guinness Book of World Records. So that's a little picture of the certificate that they got. So that's kind of interesting. I don't see that often. So there's the record, 80 attoseconds. Now, you can ask, well, why are we doing this? It's kind of cool, but why are we really doing this? So now, yes, this slide is too complicated, too late in the presentation to make sense, but let me just make 2 quick points for you. These attosecond pulses really represent a completely new set of tools, utterly new set of tools to do time-resolved metrology. So if you look at sort of the timescales of processes, and you say, oh, well, what's the sort of atomic motion in molecules and solids? Those tend to happen sort of in the picosecond timescale. And on the other hand, if you look at electron motion in atoms and molecules, those happen really in the sub-femtosecond to attosecond timescale. In fact, it takes, just to give you a sense, an electron to go around sort of the hydrogen atom, that's roughly about 100 attoseconds. to give you a sense of how long these things take. So you're really you have sort of these flashes that are lasting shorter than that. So now you can truly, for the first time, do sort of real-time, let me say, movies of electronic wave packets as they do things in atoms and molecules. And what's potentially really interesting is that these timescales, and it's hard to see, but on the bottom, these are sort of the same timescales for collective motion of free electrons in condensed matter. So things like plasmons and charge transfer. So now we have in front of us a whole set of tools to do some really, really interesting physics. And I think it's going to change the way we look at these processes. So now, what are we doing in here? So right now, remember I talked about how, well, to actually generate these things, you have to do some engineering of the driving laser field. So this is an effort from out of MIT by Dr. Kurtner, where they're doing just that. And I'm not going to go into it in a lot of detail, but they essentially have coherently mixed two high bandwidth pulses that are sort of spaced in wavelength, and they mix them together, generating essentially a 2-octave sort of bandwidth space. And they've been able to sort of mix it in a way that generates sort of a single waveform. And the goal here is to engineer your waveform to now, because you have all this bandwidth, you essentially have 2 octaves of bandwidth, to have extremely fast transients in your waveform. So the synthesized waveform that they did here, again, they combined sort of 2 pulses using a technique called OPCPA, and that's not really important, but they were able to synthesize a waveform that has a little feature here that is sub-cycle. It's a 0.8 cycle feature. And the goal would be like, hey, if you have these fast transients, then that feature alone is going to be the one responsible for generating your attosecond pulse. And this is exactly what they're trying to do right now. You can sort of compute and you can sort of calculate that such a waveform would directly support the generation of a 150 attosecond pulse with not a lot of very complicated polarization gating techniques that you put around this. What's I think even more interesting, and again, you can just take my word for it, by using a concept, this OPCPA technique to generate these pulses, this leads to the ability to do this at very, very high rep rates. So this is potentially a pathway to have a very high average power source of attosecond pulses. Because when you want to do things in condensed matter, at some point you're going to want to have that rep rate. So this is very interesting. Okay, so let me now bring the talk to a close, and let me just remind you what it is that we're trying to do. So again, to repeat ourselves, we really want to look at the various properties of ultrashort pulses and examine sort of the assortment of phenomena that interacting with matter that's opened up. And in fact, we want to look at sources that have extreme temporal, bandwidth, and peak power characteristics. And this sort of naturally falls into sort of 3 sub-areas. One of them is optical frequency combs, then high field laser physics, and then attosecond science. And then here below, for your reference, is sort of a set of bullets. Again, I'm not going to go through them, but these are sort of the technical challenges and the open science questions that we're going to go after. So with that, I'll conclude, and I'm happy to take any questions. Yeah, good.
So, are there any questions? Yes.
So when this stuff first came out, there were claims made that there would be novel interactions between the pulses and materials, and in fact cause more rapid degradations of materials and that sort of thing. Has any of that ever panned out, or are we still firmly?
When this came out, you're referring specifically to
ultrashort pulse lasers, femtosecond lasers.
Okay. So the question is whether or not these things degrade materials and so forth.
Enhanced killing.
Enhanced killing.
Enhanced degradation of material.
Well, I think, so this issue of the laser-solid interactions, I think it's something that needs a little more attention. And depending on sort of the application that you have in mind, I think there's different answers for that. So for example, people are seeing a lot of interesting femtochemistry at the surfaces of these things. When the surfaces are exposed to these high electric fields, they're just seeing some photochemistry that's unique. And in fact, they're seeing degradation of materials with where you didn't really expect it. You're seeing deposits and so forth. And part of, I think, one of the things that I didn't talk about that we want to look into is how do you make optics that are more robust to these electric fields? because you really need to tackle that problem. And that is a material science problem, but you got to combine the effect of these electric fields on the surface. So, but if you were to do that now, because I mean, these things need to last. And right now, after some time, especially the gratings, the way you compress these pulses, you have these really large gratings in these compressors. After some time, they get damaged. And it's just deposits that, even though they're in extremely high vacuums, things are changing, chemistry is changing on them. So I'm not sure that's a full answer. I'd love to talk to you about it offline, but that's one thing that I think it's of basic research interest.
Any other questions? There's one in the back, hang on.
In terms of material degradation that you're talking about,
yeah.
Actually there's a phase between the solid and the plasma called the warm dense matter. Does that come into effect, any of these?
So the interesting thing is that when you're actually interacting with solids, so a lot of the experiments that you see that I talked about, you do them in vacuum. So you have your surface, you have your laser, and there's nothing in between. But in reality, if you're going to do something, oftentimes you have air in between, and air is going to react. So air now becomes part of the equation. So oftentimes, before your laser actually gets to your surface, you've actually created a pre-plasma of the air, and that's going to completely change your dynamics. So you have to take that into account. So yeah, this whole thing is really, it's multi-scale, both in space and in time, and it's complicated. So yeah, but it definitely affects it.